Hello, my name is Xiaoyun Zhou from Harbin Institute of Technology. I'm glad to share this work, which is about running deep neural networks on resource-constrained platforms. Deep neural networks have been widely applied to many artificial intelligence tasks in various fields. To further improve the data analysis capabilities by increasing the inference accuracy, DNNs have been more deeper and more complicated. However, applying a complex DNN on these resource-constrained devices is challenging, such as IoT devices, mobile devices, and smart wearable devices. For these devices, the hardware resources are extremely limited, including storage, memory, and so on. Therefore, we design a framework called Smart DNN to reduce the memory requirements during running DNNs. Our work is based on several observations and motivations. On the one hand, we learn that running neural networks is layer by layer, and such computations on one layer do not rely on other layers. On the other hand, we analyze the memory overhead of running a neural network on several popular neural network frameworks and found that the memory overhead mainly includes two parts. The first one is the parameters of neural networks, and the second one is the intermediate feature maps of neural networks. According to these observations, our work employs an error-bounded lossy compression technique to reduce the neural network size. And when running a neural network, we first load the compressed network to the memory and partially decompress some layers as needed, execute the computation on these layers, and immediately release them. The core idea of Smart DNN is shown in Figure 2. Here, the memory cost includes two parts as we mentioned. The first part is related to the network scale, and the second part is caused by the network running workflow. Instead of maintaining the whole network and the feature maps in memory, Smart DNN only keeps compressed network, partially decompressed layers, and the corresponding feature maps, and then reduce the memory cost. For the compressing technique used in Smart DNN, the general workflow is shown in Figure 3. We apply error-bounded lossy compression to compress neural networks, and a larger error bound usually means a bigger accuracy loss but a higher compression ratio. Therefore, we aim to make a better balance between compression ratio and network accuracy. We first select an error bound for the whole network as a baseline, and we slice the neural network into several segments and get the best error bound for each segment. For error-bounded lossy compression, we follow the idea of SD compressor. Parameters in a neural network are regarded as a float point number stream. Specifically, we denote the neighboring float point parameters in a network as di and di minus 1, and the value of parameters can be calculated and quantized as the first formula. Here, epsilon is the predefined error bound, and mi is the quantization factor for recording the lossy difference between di and di minus 1. In this way, difference in between neighboring parameters all will be converted to integers and can be easily compressed. Similarly, we can recover the compressed parameters according to the second formula. The compression ratio depends on the predefined error bound, which also impacts the inference accuracy of DNNs. Thus, we could set a reasonable error bound to maximize the compression ratio of a network without significantly reduce DNN's inference accuracy. Figure 4 shows examples of studying the impact of the error bound on four well-known lightweight DNNs. Generally, the results demonstrate that the lossy compression in smart DNN can achieve a high compression ratio on DNNs, but cause uncertain impact on the inference accuracy when increasing the error bounds. Therefore, we consider two key metrics in smart DNN, the compression ratio and the inference accuracy loss, and design a flexible solution to meet the user's various requirements on the two metrics while strictly ensuring the inference accuracy loss is acceptable for DNNs. Specifically, we calculate a score for each error bound and select the best one which does well on both two metrics. Considering that our method is to access the neural network layer by layer, so we design a way to compressing the neural network in several segments to further improve the compression ratio. Figure 6 shows the accuracy under different error bounds on different layers. According to the results, different layers have different sensitivities to error bounds, and the larger error bound will make more accuracy loss on earlier layers. Therefore, we design a method to divide the neural network into several segments and select the most reasonable error bound for each segment to pursue a higher compression ratio as shown in algorithm 2. We use the score to assess the compression efficiency to select the optimal error bounds for each segment in DNN, satisfying users' requirements on both the compression ratio and the inference accuracy of DNNs. We conduct our experiments on 4 popular lightweight neural networks and train each of them on CIFAR-10 dataset. Table 1 shows the compression ratio results of smart DNN and other approaches on 4 DNNs. The results suggest that smart DNN achieves up to 3.4 times higher compression ratio compared with the DeepSA. For memory overhead, we compare 3 approaches. The first is the trivial solution. The second is smart DNN, and the third is only running DNN layer by layer without compression. Table 2 shows the memory overhead and the running time of these 3 approaches on the 4 DNNs. The running time of layer by layer is the highest among all 3 approaches, and it is about 3 times to 5 times than the trivial solution. Even its memory overhead is the smallest. And our solution, Smart DNN, has a good balance between memory and running time. The running time overhead is much smaller than the layer-by-layer approach, and the memory overhead is also reducing significantly compared with the trivial solution. More evaluation results are discussed in the paper, and these are all content of my presentation. Thanks for listening.